Yeah, can start now. Hello everyone. Yeah, today my throat is bad, so I'll be sounding like a frog. So don't mind that. Yeah, today we'll continue the topic of safety. Safety will continue. Some aspects of it, because most of the things have been covered by Sudhir Kumar. As I was telling yesterday, what happened?
Got disconnected.
Okay, so we have failures, which is represented by lambda, the failure rate for the total system. Then you have two kinds of failures in this. A failure which can be safe, a failure which can lead to an unsafe situation. We saw that unsafe means accidents. Then in the kind of category of safety failure, you can detect the failure detected and undetected. What happens? It's a safe failure. Failure does not lead to any disaster. It is a safe failure, but it can be detected, or it may not. You may not be able to detect what happened. What happens in case of detected? You repair it. If you detect it, you repair. This is where maintainability comes in picture. You repair it, how fast, etc., etc. Undetected failure, the MTTR is very high. MTTR goes high because you take a lot of time to find out where is the failure. MTTR goes high means what? Availability goes down. This is implication of a safe failure. The safe failure affects your availability ultimately. In the case of a detection, the availability is you fast you repair, so availability is high. In the case of undetected failure, the MTTR goes high because you don't know what to do, where is the failure, what is to be replaced. But system is not in an unsafe state, so you take time, so the availability of the system goes down. This is the implication of safe failure. You have undetected the unsafe failure. Unsafe failure again can be detected or undetected. So I will call this as lambda S. This is lambda safe detected, and this is lambda safe undetected. U undetected. So this I have unsafe. That is a dangerous failure lambda. Here lambda dangerous failure detected. As in this case here, this also detected. The lambda dangerous failure undetected. So we'll see this branch now. Lambda, the failure rate of dangerous failures which are detected. Again, you can take action. Once you detect, you can design a system how to deal with it. So this what is yesterday we saw as safety related systems. This we implement a safety related system which takes care of, it detects a dangerous failure, it shuts down. Yesterday I gave an example of a motor. The temperature goes up, the thermostat detects, shuts down the thing. Here the thermostat is the detector, so it's an unsafe failure because ever if you allow it, the temperature will go high, the motor will catch fire and danger. So it's a detected failure. And how do you deal with detected failure? You deal with the safety equipment, safety process. So we saw yesterday generic name, safety related system, SRS. Okay. Now come to the undetected failure. Undetected failure is the disaster. Is the disaster. It is dangerous and undetected. So it will lead to a disastrous situation. Loss of property, loss of life, anything can happen. An explosion can happen, anything. Collision can happen in the case of a train. So if there is an undetected failure in the system and which is not safe, then it is a problematic failure. How do we deal with the safety? Totally deals with these two. That is lambda DD and lambda DU. DD, what you do, you find out methods, you know, you have detected it. There is a failure. The temperature is going up. So you can do something. Undetected, nothing you can do. Because you yourself don't know whether there is a failure or not. So it is going to lead to a disastrous situation. So what is the way out for this? What do we do? This is a worrisome case. This is a worrisome case. So the only option you have got is keep it as low as possible. As low as possible. That means the failure rate, the failures per hour should be very, very low. So this is given by the SIL level, the safety integrity level. So SIL 1, 2, 3, 4, 1, 2, 3, 4 of the SIL levels define, quantify how much this undetected failure, unsafe failure can be. How low? 10 power minus 9, 10 power minus 8, 10 power minus 5, minus 6. We'll shortly see that. So this I drew the picture just to introduce you how failures can affect your availability. In this case, availability in this case, designing a safety related system in this case, and minimize the disaster in this case. So all have their origin to a single fact, which is a failure. In each of these branches, you do something, activity. Some are maintainability and some are safety. These two categories comes under maintainability issues. These two categories comes under the safety issues. So today what we are going to see is, having said this, today what I will introduce is, I'll just quickly go through the few nomenclatures we saw yesterday and just elaborate on that and go through the brief contents of the standard which I told you, 61508, though it is not very relevant to us because that is a mother standard from which 50129 was derived. Our standard is 50129. So 129 is available in the website. You can take it and you can just go through what it contains. You don't have to memorize everything. Because when you practice, you will have book to see it. So, but you must know what it contains, what to look for in 50129. Right. So, having introduced the failure and the relation to safety, now we will see so in the case of undetected failure, in the case of lambda, dangerous, undetected, the last limb. And in the case of lambda, dangerous, undetected, the last two limbs. To handle it, first let us say the detected one, we said we have a SRS, safety related system. So this is where, in relation to this, we defined the word yesterday. I don't know, I don't remember I have said it. One is the functional safety. There is a word called functional safety. Second is safety function. Third is safety related system. And in the case of undetected one, we have the SIL. So these two failure categories are covered by these four topics. This exclusively goes for lambda, dangerous, undetected. And these three, what we do, these three of them deal with lambda, dangerous, detected. They do this. Okay? Now we will see what are these words. Functional safety, safety function, safety related system. These three we will see. One second, I misplaced my. Yeah. So first we will do these two words. It's very important word. Functional safety and this arises from safety function. Now when we say functional safety, automatically a question comes to our mind, is there any other safety? If it is only one safety, then why not call it safety? Why functional safety? So there is another safety which is not our subject today, inherent safety. And this is the functional safety, FS for functional safety. I don't have space in my board. So this is functional safety. What is inherent safety? Will example we will give. You have a tank which sends dangerous chemicals and sends out for a process. This process. This is a chemical storage tank. The chemical, whatever chemical is very dangerous. And there is a pumping machine here which pumps it into this from a sump or anything. Now, this is a dangerous chemical, should not leak. As long as it goes into the process, it will work, no problem. But if it overflows this tank, it excess, then what you do? One method of doing is, I have a drain outlet, I have another tank, which is called a containment tank. So any excess comes, it will just go to this containment tank and remain there. And from there I can use it. It's a very simple concept. This safety is inherent safety. I do not have any active process, active element to curtail this unsafe condition. I simply have an excess outlet. If the chemical flows, overflows beyond what it can take due to any reason, it goes into another outlet and gets storage in another tank. So the dangerous chemical is contained. It doesn't go out. This is the simple design by which I can achieve inherent safety. Now, then what is functional safety then? The functional safety is, instead of this portion of having a passive containment tank which takes the overflow. What I do, I have the tank here, main tank. I fix a level detector. This is level detector. Same other things continue. The process continues. The motor pumps in, it comes in, it goes out. I have a level detector. So the level detector just detects this level. If anything goes above this level, it gives an alarm. It receives a signal. The signal is processed by a computer. Computer means it's a microcontroller kind of a thing. And then what it does, its output goes and shuts down this valve into the inlet. So the level doesn't go beyond this point for any given condition. If it goes above, this circuit comes into this subsystem comes into picture. Please note, level detector is an active device. The computer is an active device. It will have amplifiers, controllers, diodes, whatnot, resistance, capacitance, plus active elements. Active elements means ICs, etc. Then there is actuator which will close the valve. This again is an active device. You send current, it will close, solenoid will get activated, it will close the valve. So this loop, which this also achieves the safety of the system. So this is called the functional safety. Functional safety. Basically, it has to do with an active system, an alarm system, for example, a fire alarm, smoke detector. These are all functional safety elements. Okay? Then we come to the word safety function. Safety function. In the case of the tank, I said there is a sensor which does the level. There's a controller which decides the output to be given or not. Then there is an actuator which closes the valve to stop the flow into the tank. These are all involved. What is the purpose? Their purpose is to carry out a function. They carry out a function. They carry out a work. This function is called the safety function. The difference is subtle, but I will elaborate to make it clear. This, what they do, this function is safety function. Why can't we stop with this safety function? Why again say functional safety? A complex system like the railways or a project or a chemical this thing will have many safety functions. We may have to control the overflow in the case of a chemical process. You may have to control the pressure. You may have to control the temperature. Like this, many things. This will have, this is a safety function. This is a safety function. This is a safety function. This is a safety function, a safety function. This is another safety function. I will have another sensor, another controller, another actuator, another outlet, output device. So these are all safety functions. So the process will have many safety functions, but the process running safely, this will, all of them together is the functional safety of the process. Functional safety of the process. For example, in the case of railways, you will get the idea. I have, yesterday I gave a thought process problem. I have the station. Which has many signals. These are all signals. There is a point here, there is a point here, there is a point here, point machine, there is point. All these functions are available. I connect all these things by cable. You know, if I want to move, so I connect everything through a cable. All functions, all these devices through a cable I connect. I bring it to a panel from where the SM sits and operates. He has knobs and switches in the panel. He operates this. This is how the physically the system looks like. So far, nothing, no departmental bias. I have points, all of you know. I have signals, you know. I have a track, you know. So the point machines have to be controlled. So I connect everything by a wire, bring it to the some station master's panel, which you must have seen. He has got knobs and things like that. In addition to that, please remember I have track circuits. They are also brought. So there are many things which are brought to the. So here, what is the functional safety? And what is the safety function? This is the question. Can we do with only one definition of safety function and leave it there? Or do we need a function? That means the functional safety will have for the entire system, which is this. This is the entire system. It is the safety of this entire system is functional safety. Then what are safety functions in this? The safety functions are one, the conflicting interlocking. If a train comes from here, another train should not go from here. This is a conflicting move on the same route. So the interlocking, some equipment behind the panel will be there. That will be from here, we go to the interlocking equipment. So that will make sure that I don't send the train onto the same track section at the same time. So there is an interlocking function. And this, I'm sure you will all agree with me, it's a safety function. It has to do it very safe. This is one safety function. But this is not the only safety function it does. If it has been the only safety function it does, it makes no difference whether it's a functional safety or safety function. Can you think of other safety function it does? Look at these wires here. From the station master's panel, there is some connectivity to the processor. It is again a cable. There's a cable here which connects to the processor to do the design. And that's how he gets his command goes to this, and then from there it goes to the field. He gets an indication, he has a blinking, he has a red color, he has white color, green color, everything comes. So there is another function which is the display and control function between the panel of the station master, which is the human operator here, and the interlocking. So this also need to be safe. May not be to that degree of complexity that no conflicting moves should be permitted, but he also should, if the signal is showing, let's say green, he should not get an indication red here. Nothing dangerous will happen, but there will be confusion in the mind of the fellow. I have taken off the signal to green, so he expects the green to come on the spot, but he gets only a red, doesn't change. That's because there is some problem here in this wiring. So this is another function, safety function. So there are two safety functions in this. Like this, there are many safety functions I can design, I can describe, for example. So let me finish the second one. The second one is the indication from the processor to the station master's panel. It is also a safety function. May not be as severe as the first safety function, which is the conflicting movement. So this is the second safety function. So I have safety function 1, which is conflicting move to be avoided. I have safety function 2, indication to the station master. Safety function 2. I can describe another safety function. I send a command to a point to be going to normal or reverse. Then I read back, has it been done all through this wire it comes. Now if the point goes from normal to reverse, the indication should come as again like from normal to reverse to this part. There is no harm. But the point does not go from normal to reverse. It does not go here. But the indication comes here as it has gone to reverse. Then the processor will presume, yes, it has been done accordingly. So the signal will come. The route is for this because the point has not moved. But this fellow will give the route as this because the point is still in normal only. It has not gone to reverse. The reading comes as reverse. So this is again a safety function. So I must read and my command has been obeyed or not in a safe manner. If I don't read it in a safe manner, then my whole argument of conflicting moves goes wrong. So this is another safety function, third safety function. Similarly, I must read the track circuit is up or down. I must correctly read. This is a safety function. But these are all high integrity safety functions. A conflicting move, a point is in normal or reverse, a track circuit is up or down. These are all high integrity safety functions. That means the level of integrity of the information I get should be very high. It should be truth. It's almost to truth, nearing truth. If it is normal, I must get as normal. If it is reverse, I must get as reverse. If it is up, I must get as up. If it is green, I must get as green. So these are high integrity safety functions. Some indications to the panel which I described, the second one, it may not be that high integrity. It is a safety function, but there is a different level of integrity. When I say integrity, the truthfulness, or how correct, how good it is, how much can you rely on this? So all the safety functions, 1, 2, 3, what I have described in the railway environment, put together is called the functional safety. So now understand the difference between safety function and functional safety. Safety function is a subset, is a group. A system will have many safety functions. So, but I will say only that the functional safety requirement of the station interlocking should be fulfilled. When I say the functional safety should be fulfilled, I mean that please find out what are the safety functions. This has to do, identify each of the safety function, identify each integrity level of each safety function, and then design accordingly. Then you can claim, yes, I have achieved functional safety for this whole system. For the whole system of here, I have achieved functional safety. So this is all about functional safety. Now next. The safety will be assured for the entire system only if all these safety functions I have described, all these safety functions work when needed. This is the statement I'm making. This is the summary of the statements of whatever I explained. The safety of the system will be assured only if all the safety functions, 1, 2, 3, 4 I described, work when needed. That means they must work and they must, whenever you need, it must work. This when needed is as important as the work. So two words I've used. The work means they must function. When do they function? Whenever I need. Whenever I want the point to change the reverse, it must work. Whenever I want the indication to come, it must come. Whenever I want to send a train, the conflicting move should be decided. So when needed, now this leads, this word when needed, this brings us to the concept of demand. When needed means when demanded. So the concept of demand comes from this. The safety should be assured only if all these functions, the safety functions, work when needed. So this when needed leads to a concept of demand. So in the case of functional safety, the concept is what is meant by demand. When do I need it? So the IEC 61508 describes two types of demands. One is low demand, other is high demand, or it can be even continuous demand. Continuous demand. Okay. What is this low demand and what is this high demand? The low demand. Once in a while, I ask the safety function to work. Once in a while, not every day. For example, the tank overflowing I showed you, there is a safety function. There is a safety related system with actuator, valve, controller, etc. So they may work once in a while, maybe once in a year, once in 6 months. That is the time the overflow will take place. It's not going to take place every day. So that is a low demand function. Have you heard of the airbag in a car? The cars these days come with an airbag inside. In case of a collision, the airbag pops out so that you are protected. That is a low demand. Because every day the car is not going to collide. Maybe once in a year, once in 2 years, and maybe once in the lifetime of the car. So this is a low, but it's a safety function because it has to come to save you. So this is a low demand safety function. What is the high demand? Very often you need. For example, the brake system in the train. It's a high demand safety function. It has to be a safety function. You apply brake, the train has to stop. There is no way you apply brake and nothing happens. So it's a high demand safety function because we don't know how many times you will do. You may do every station, you may do once, in between station you may do once, in the level crossing gate you may do. So many times you will apply the brake in the journey of the train. Maybe once in half an hour, once in 15 minutes you may need. This is a high demand. And what is continuous demand? Continuous demand, all the time I need the attention. The interlocking is a continuous demand. So many trains will keep on passing. Every time I'll keep changing. Every time I'll keep changing routes. So this is a continuous demand. So the interlocking function at the station is a continuous demand. Now the question to you is, the ATP system, is it low demand, high, continuous? Which category you think it will come to? What does ATP do? The driver is the controlling element. He drives. Whenever he exceeds his speed, what is permitted, or whenever he tries to cross a danger signal, it should come into action and stop. This is a function of the ATP, in simple words. Whenever either exceeds the permitted speed or he crosses a red signal, it should come into action, apply the brake and automatically stop the train. This is the thing. So it all depends on now. To decide on whether it's low or high or continuous, it depends on the controlling element, which yesterday we defined the word equipment under control system, use CCS. In this case, it is the driver, let's say. Depends on the reliability of this guy. The driver's reliability. If he is very attentive and if he doesn't fail to act, no problem. ATP never comes into play because he is given a profile of the speed and he will continue to operate below the profile of the speed. He is repeat this, the cab signal repeats the signal aspect. He sees red, green, yellow, and he just acts according to that. So if he is a very reliable driver, the ATP demand may not be there at all for months together. But if the driver reliability is very poor, and he just fellow talks on cell phone, sees here, sees left, right, he doesn't see the speed profile, doesn't see the signal, then the ATP will keep on coming into action to control the speed of the train. So it depends on the control system which controls the equipment under control. The control system here which controls the equipment under control. It depends on the control system's reliability. In this case, it is a driver is a control system. Who controls the train? It is a driver, yesterday we saw. It depends on his reliability. So depending on that, somebody can say it is a low demand system. Somebody can say it is a high demand system. Somebody can say no, it is a continuous. All the time it has to watch. Every moment it has to check the speed. Every month see whether it is over. So what will you choose? When you are asked to decide, which one will you choose of this? You don't know anything about the driver. Which drivers will come, we don't know. There are hundreds of them. How each fellow is reliability, whether he is good or bad. So which one will you choose? If you choose a low one, the cost is going to be cheap. You can win the tender. If you choose these two, either of these, it is going to be costly. Because the integrity level has to be more, I said, in the high demand case. Yes, more often it is needed, so it should not fail. So when I choose, if I am the designer, I'm giving an offer. So I can give a cheap offer, taking a low demand, and I can win the contract. If the specification says it's a different matter. It says it's a high demand profile, you have to design. But the specification doesn't say that. It is left to you. You are the integrator, you decide. So the management will say, you go for this, you will win the tender. But you as a professional will say, look, I don't know, 100 drivers, how they are. 99 may be good, one fellow may be bad, he can cause the accident. 50 may be good, 50 may be bad. 50% of the fellows will cause accidents. So I would like to design a higher continuous demand system and give the offer. So here actually you are in a big dilemma. Because the management wants to win the tender by going for a cheap design. You have a conflict. Look, what I'm doing is not correct because I don't know about the drivers. That information is not with me. But I'm asked to design. It's not correct. If I low demand, if I design, I will cause an accident. Professionally, you feel bad. No, this is not correct. So it's a question of ethical choice. What do you want to do? Any comments?
Okay. So Akila says continuous.
Yeah, that is a failure on the safe side. So you should say, okay, you should convince. You do not know about the drivers. We will get a bad name. If we cause one accident, our whole market will collapse in future. I will go for a continuous demand so that I fail on the safe side. I presume even if one driver is bad, I take care of it. Our equipment will work without causing an accident and we get a name. And if you go for a low demand, you may win this contract. Next month, you get cause an accident. Yeah, forever your future contracts are gone. So this is how you will argue to your management and say, look, let us design for a continuous demand system so that we keep our name and we say, yeah, this guy's equipment is good. So let us use it forever. So others also will believe you. So this is the kind of conflicting things comes in the design of the safety functions of the equipment. So we go for this continuous all the time. So that is the safest design. Now then why have the standards, the whiteboard. The whiteboard, are you able to see it? It does not exist. 1 minute, I will send an invitation, Benai.
Okay, sir.
The whiteboard is gone. I have sent it.
So it's not asking for the password.
It's not asking for the password.
No.
So it's not coming.
No,
You're not able to see anything?
We have not logged in, sir.
Okay, so what do we do now? Minute. One second. Just 1 second.
Okay.
Start afresh. I have loaded the whiteboard. I'm sending you the invitation. Now you see.
Yes, sir.
Okay.
Yes, sir.
Right. So we have seen the demands when needed. So we answered the question when needed. In other words, leads to what is meant by demand. Now this brings us back to the question of failure. A failure, no failure system will always be available whenever you demand. A system which is prone to failure, doubtful when it is available or not. So to address this, the standard 61508 tells us what are the techniques. I'm not going into details. What are the techniques to achieve this demand? What are the targets of failure which are needed for the demand? What kind of tools you must use to achieve these tools? Means in this case is a software tool. Then what are the other standards of functional safety? Standards of functional safety. So this gives all this. ideas. What is the demand and how to meet the demand. What kind of failures can happen? You can have a random failure, which we have dealt for so many classes. We'll have systematic failure. Random failures are hardware oriented. Resistors, capacitors, diodes, transistors, anything which is failed, valves, gasket, spring, these are so many things. Hardware, anything randomly it fails. There's no reason or you can't find out anything. And you can mathematically model, we have seen so many models, distributions, and hardware is no problem at all. We can find out what will be the failure for a given configuration. The systematic failures are human oriented. Human oriented means what? In the design you make a mistake. In the software when you write you make a mistake. So these are not possible to quantify. No model exists how a human being's mind will fail and you will fail in your design. There is no model which is existing. Then how do you do? If I have to control, the standard says I will control the failures by techniques, tools, standards. Techniques for hardware is known. Exponential distribution, Weibull distribution, all sorts of things we have seen it, how to fix it. What is the probability of failure for a given system by RBD, FTA, all those things you can do. Systematic failures, there is no model. So what do you do? How do we control systematic failures? The standard gives us guidance. What you do is, systematic failures, how the standard gives guidance is, if you are writing, so let's say design, the hardware design part of it. There is one person who designs. The standard says you must set up a hierarchy of design organization. There is a second person who checks. There is a third person who does another independent checking. There is a fourth person who approves or recommends. And there is a fifth person who approves. The standard only says your design office should go through this process. You cannot have one design engineer who will design, who will approve, who will issue the drawing. The standard does not permit that. So the independent safety assessor who comes to see whether the system is safe or not, he is not going to do all calculations. He will come to your office. Please tell me, your design office, what is the organizational setup? That I'm sure Mr. Sandeep Kumar must have taught you those things. It is purely systematic failures can be tackled only by evolving methods of management. How do you manage the design office? In the case of a design, you will look for organizations so that there is one check, one fellow does, another independent check, third independent check, and fourth independent check and final approval. So if he makes a mistake, either this fellow will catch that, or this fellow will catch that, or this fellow, or this fellow. Somewhere you will catch there is an error here. And then what else you do? You design things to standards. Design to standards, not from your mind. Like if you want to design a spring, the material you want to choose, what is the tensile strength, to what standard, is it ISI, is it BSI, it is American standard, what standard material to use, all those things will be brought into the picture. So the ISI will only ask, to what standard have you designed? What is your organization? To what standard have you done? Is the designer overworked? Is he work only 8 hours a day? Or is he working 12 hours a day? Then you will suspect, if this guy is working 12 hours a day, you want to cut cost by reducing the number of designers you use by putting each one 12 hours a day, is likely to make, his mind is likely to make more mistakes, origin itself. So he will ask all sorts of questions like this and then satisfy himself, yes, in design, systematic failures can be reduced to the minimum level because this cannot be found by any equation or any modeling. Similarly, for software, remember the SRS, there is a controller, I said. The controller has maybe a small bit of software, maybe a very big software. A lot of lines maybe there are a few lines, but it will have, these days nothing works without a software. So the software team has to be, how is to be organized. Again, the standard says different methods, who will do the coding, who will check, are they independent, are they dependent, who will approve. There's a big chart which gives how do you organize your software organization. If you don't, if the ISA comes for checking, ISA is independent safety assessor, when he comes for check, he's only going to look at your organizations. As the code has been verified by a different fellow who is not under your control. The fellow who writes the code is under my control. The fellow who verifies the code is not under my control. He doesn't report to me. He reports to some other boss so that he doesn't have to be afraid of me and say, okay. So the independents are recommended in the standard. The standard very clearly says recommended, highly recommended. HR and R, the word is recommended or highly recommended. So as the integrity level goes up, as the integrity of the safety related function SRS goes up, that loop, the controller, input, output and all. As the integrity level, you want a higher integrity demand. Your organization has to be more and more independent and multiple checks, etc. etc. So systematic failures are basically avoided by management methods all the time. Documents. One important fact of avoiding systematic failures is good documentation. Who has done the design? Sudhir has done the design. And which year? So you will sign and put it there. So I go back after 5 years, I say I should be able to trace it back. The original design was done by Sudhir, checked by Arman, approved by Akila. So all this should be available there. Even after 5 years, I should be able to go back. If there is any modification, it was modified by X. The modification 2 was done by Y. Modification 3 was done by Z. So all will be recorded. So I trace the document where the mistake has happened. The person may not be available, doesn't matter. But when the mistake has happened, at what stage? Is it in the second stage, check the mistake happened? Is it in the first stage or it in the third stage? Where has it happened? Or all of them have made a mistake. So documentation is very, very essential. And so the ISA will see for the management methods, the documentation available, which is called traceability. Which he must have taught you. The traceable, I trace anytime, not just I design and throw it and approach no records available with me. No, I don't know. 5 years back I designed, I don't remember. But your office should have all the records to trace back what had happened. So traceability they will see. So this is how you avoid systematic failures. And systematic, please note the name spelling systematic. Systematic. There is another word why I am saying is, you all know there is a word called systemic. Systematic. Systemic is, not relevant here, but I'm saying you should not use this word systemic failure. Systemic means the whole thing is failed. The entire organization is stupid. So nothing, and you cannot have such organization. So we don't do what. So we are talking about systematic failure, where by management method documentation you can do it. Now, it's a random failure you do by mathematical modeling. Systematic failure management organization. So if you do these things properly, then I get the system which is of high integrity. High integrity means what? Whenever I need, whenever the demand arises, it will work and it will work correctly. It will not fail. It will not disappoint me. So the SIL concept arises out of this. It is a measurement of SIL is a measurement of the reliability of safety function. Please note, I have used the word safety function and not functional safety. I will elaborate on this. The measurement of reliability of safety function. It is a measurement. If it is a measurement, then I must have an instrument. Is it not? Then only you can measure. But still is not measured by an instrument. Easiest way is to measure is just design an instrument and measure it. As I said, still cannot be measured, even though they use the word measurement, because the random failures, yes, I can measure, I can forecast, I can do mathematical modeling and say, okay, this is going to be like this. Since it has got an element of systematic failure, which is basically a management and documentation methods, there is no way of measuring that. There is no model exists, so I cannot predict. So there is no input-output relation there. So that is why, though it is a measurement method, the standard 61, what happened to my board? Oh, 6150, 508 allocates the SIL levels. It says SIL 1, 2, 3, 4. 4 SIL levels are allocated. Since it cannot be measured, though the word used is measurement of reliability, or you can say it gives an indication of the integrity of the safety function, how good it is. So the standard allocates 4 SIL levels. This is the lowest SIL level and this is the highest SIL level. And then it gives, there are two. One is what we call the probability of failure on demand. We came to the concept, when you need, it must work. If it doesn't work, there is a failure. What should be the probability of a failure for a low demand system? And for a high demand system, they don't use the word probability of failure on demand. It is probability of failure per hour, PFH. Because the demand is so high, there's no point in saying that on demand. The demand is coming 100, 200,000, 10,000 times. So per hour, what will be the probability of failure? What will be the failure when a demand, because the demand is once in a year. Now, a word of caution here. There are tables available for this. For example, SIL 2. I'm not writing all those things. You see, it will be available. SIL 2 low demand is failure is 10 power minus 3 to 10 power minus 2. And SIL 4 is 10 power minus 5 to 10 power minus 6. This is the probability of failure on demand. 1 is 10 followed by 4 ciphers. For a low demand system, it is like this. For high demand system, the probability of failure per hour corresponding here is 10 to the power of minus 9 to 10 to the power of minus 8. Probability of failure per hour. Just a word of interesting feature is, this is failures per hour. This is probability and demand. Now, let's say this demand they have described, I think the standard says is 1 per year. The demand is 1 demand per year. Now, a year how many hours? Almost 10,000 hours. Isn't it? 8,000 hours in a year. So let us take 10,000. If this probability of failure per hour is 10 power 9, minus 9. So in a year, how much it will be? It will be almost 10 power minus 5. The same as this. There is no difference between these two. But this is given, your design will be to this 10 per hour basis. 10 power minus 9 to 10 power minus 8 is the highest cell level. We said cell is a measurement of the reliability of the safety function. I said I use the word safety function. I have not used the word functional safety. Why? A system will have many safety functions. I gave an examples of the railway interlocking. It will have many safety functions. So some of the safety functions can be SIL 4, some can be SIL 3, some can be SIL 2, some can be SIL 1. All need not have the same SIL level. The interlocking solver, the Boolean algebra solving equipment which is inside the computer, will be to standard SIL 4. The indication panel between the station master and the microlock or the interlocking equipment, where only indications flow. Wrong commands cannot be carried out because that is to SIL 4. That can be even to SIL 2. The point detection, whether normal or reverse, it has to be highly integral because a disaster is bound to happen. That can be SIL 4. So I said this is the measurement of reliability of a safety function in a process. There will be many safety functions. So each safety function you have to look at and say, I want this SIL because of this importance. So that is why it is safety function. It is not for the functional safety is the whole thing, all safety functions together. So the SIL is for a safety function and not for functional safety. Okay. Similarly, SIL is not for a device. It is not for the transistor which you are using. It is not for the capacitor you are using. It is not for the IC you are using. It is for the safety related system, the functioning of the loop, sensor, processor, output control. This loop, it is an active loop. So it is for which carries out the safety function. The SIL is for the function, not for a device. If somebody asks you a question, I've got a so-and-so mill standard IC I'm going to use in this. To what SIL should I use? Your answer will be, SIL is not for a device, it is for the loop hole. There has to be a sensor, there has to be wiring, there has to be a microprocessor, there has to be an output. How do you wire? How do you clip the wires? Everything is described. So the process, the whole function, only I can allocate a SIL, not for the devices. I may use an excellent device and still produce a very poor SIL functioning equipment. So SIL is for a function, not for a device. And it is not for the functional safety because a functional safety contains many safety functions. Each one will have its own SIL. All may have SIL 4. One may have SIL, different SILs they will have. Now comes to the railways. The derived standard is EN, yesterday I said 50129 about safety, which is derived from 60158. Now this talks only about it went and came on. This talks only about high demand and continuous. High demand stroke continuous probability. So this has got 1, 2, 3, 4 levels. And one is 10 power minus 6, 10 power minus 5, 10 power minus 7, to 10 power minus 6, 10 power minus 8, 10 power minus 7, 10 power minus 9, 10 power minus 8. This is the range, cell 1, cell 2, cell 3. Because railways use mostly in signaling purpose, all are cell 4. SCADA may be cell 2. The interlocking indications may be cell 2 again. So most of the things, even the brake system may be in cell 3. The interlocking may be in cell 4. So all of them are in, you see the probability, this is what? This is the probability of failure per hour. And what kind of failure we are talking about? The first slide I showed you. Detected, dangerous, undetected failure. That means this is going to cause an unsafe situation. The probability of a failure which will cause, this failure here is, it is a failure which will cause an unsafe situation. Cause unsafe situation. We are not talking about the failure which will just stop all the trains. No, that failure is not included. This is only those failures which will cause an unsafe situation should be for a cell 4, 10 to the power minus 9 per hour. It's very low because it comes under the category undetected. Now corresponding to this, now this is, since we are quantifying here, this is for the hardware, for random failure I can find out whether it fulfills or not. How do I find out? I do an FMEA, do what are the hazard analysis. I think Sridhar Kumar must have taught you hazard analysis. I do a hazard analysis. I pick up all the hazards which can cause a disaster. And then if this hazard has to take place, this failure has to take place, then I follow the chain using FTA or FMEA. What is the overall, the top event will occur with what probability. So like that, I calculate for each hazard, what is the probability of occurrence. Then I do that, then I can find out my probabilities in this bracket, this bracket, this bracket, and I say, look, the system is going to be only this cell standard. And if it doesn't meet, then I look at the design. So cell is, though it says it is a measurement, but it is an allocation because it has got random and systematic. So I can do random calculation, I told you, hazard analysis and do it. What do I do for systematic? Then I refer to the standard, see the organization, what does the standard say? How do I organize my design? How do I organize my software? Everything it is mentioned here, it is recommended. So is my organization according to that? If I do like that, if I create my software as per the standard prescription, it is presumed as my failure will not exceed this. Random failure, I definitely do this. Matching this, the systematic failure also I can achieve, not by calculation, but by setting up a management process. So that is why the levels are allocated. It is not measured. One of the component is not measurable. The quantity 10 power minus 9, I have to prove to the ISA by my random calculation. Failure mode analysis, FTA, all those things I will use. I will prove to him, look sir, this my failure rate is 10 power minus 8. Unsafe, that is, dangerous undetected failure is 10 power minus 8. So I claim 10 power minus 4. Then he will put a tick mark, okay, you have achieved this for this safety function, next safety function. I will again do the process, I will show it to him. I have calculated like this, I am allotting cell 3 because I am getting 10 power minus 7 lambda du. He will say, okay, happy, satisfied. So like this, if there are 100 safety functions to be done by the system, for each one I prove this for random failures. This table is only for random failures. Then he will say, every time when he answers yes, I'm satisfied with your SIL 4 for this. He will ask, please tell me correspondingly, how have you written your software? How have you designed the system? What is your design office? So he will check that also. And he will compare with the standard and tick mark each one and say, okay, I can allot SIL 4 to this. I'm satisfied with your system, both random and systematic. So every safety function is going to look at both aspects and certify, yes, it is okay. I'm said. If it is not, he'll say, no, it is not okay. He is not going to point out what is the mistake because he is not equipped for that. And even if he is equipped, he will not tell you, where is your calculation wrong? He will say, this is a wrong calculation. I don't agree with this. Please go and do recheck. It is for you to find out where is the mistake. This is one very important aspect of it. The man who checks ISA when he comes, he is not going to tell you what is your mistake. He is only going to tell you, you have not followed the standard. It is for you to find out where is your mistake, and you are correct, and again call him, he will again check. That is because they don't want him to be a part of your design. The ISA should not be a part of your design. He should not say there is a mistake here. He will only say there is a mistake. Please check. So it's you have to rock your brain and say where is mistake. Then genuinely it will come out. Otherwise, what you will do? You will do some calculation and show him this thing. Anyway, he will check and say, no, this is a mistake. You correct here, you correct this, you correct this, you correct this. So everybody will just lethargy. ISA will do everything. So let us do some design and give it to him. So he will not say, he is not supposed to say what is the mistake. He will say, yes, this line there is a mistake. What is the mistake? You go and find out. And again put up to me. Come and convince me. So SIL, as I said, yesterday I concluded saying that today I will introduce SIL concept. I have introduced the SIL. To summarize, SIL arises out of the safety function, which is a part of the functional safety. Functional safety is the overall safety of the system, which contains many safety functions. Each safety functions can fail because of dangerous undetected failures. And what is the probability of the failures? That depends on the demand. We said for railways, the example we said, we take higher continuous demand. We refer to the SIL table, prove the random failure to that probability per hour. Then matching management and design office, we convince, yes, I have followed the standards, then I have followed a SIL level. In summary, if I say SIL 4 is for interlocking, that means it is going to fail 10 power minus 9 failures per hour. Unsafe failures, not failures. Remember, a signaling system, when it fails, when it detects a unsafe failure, everything goes to red. All trains stop. Very safe. But it is not reliable. So the signaling in the railways is designed to be like that. There are conflicting interests, but you can't help it. The signal engineer will say, I can make it danger when there is a problem. I cannot do anything else. Trains won't run. I will take the time, I will minimize the time to repair it. But there is nothing in between. So either it works or doesn't work. So there is a conflict of reliability. When you want a high safety, it will be at the price of reliability. Otherwise, there are some methods nowadays that doing redundancy, put in redundancy. I can't put 2 signals at every place. So the driver will get confused which signal to follow, which is working, which is not working. But in some processes, you can use redundancy, increase reliability. So those are techniques which are used to improve. Basically, there is a conflict between safety and reliability. This conflict can be solved through redundancy in some cases. It cannot be solved through redundancy in some cases. So this completes today the SIL concept, safety functions, functional safety, low demand, high demand. Yesterday we saw the definitions, risk, and things like that. I think I've exceeded my time, right?
Yes, sir.
Huh?
Yes, sir.
No time left.
We are already at 1 hour 15 minutes.
No?
15 minutes. 15 minutes.
15 minutes, okay. So we complete today this the safety. What I do, I just look for some problems, the very difficult problems in this. Just explain the concept, simple problems, not complicated. I will get it. If I get it, I will fax it to your office. You can circulate to them for the reading. Just to understand the concept, because it's a difficult thing. So yesterday's problem, I told you the station, panel, signals, things like that. What is UC, what is UCCS, and what is the safety related system? Any comments on that? Station control is there. There is a panel. There is an alarming system. There is a station master. So what is equipment under control there?
Music. But